Let's take a look at an example here of how we are going to use free body diagram to solve a simple structural problem. Now, in this question, it says the beam AB is pin supported at A. So we have beam AB, which is the green colored beam, right? And it's pin joined at A, and there's another pin at B because we need to apply the external load 1200 newtons through a pin which is connected at point B, and also the cable BC is also connected through the pin. It's not directly connected to component AB, but rather through a device, which is normally a pin or some sort of pin joint. Okay, so we have a cable. So we have cable BC, and a cable is a flexible element. Cable, wires, ropes, strings. They are flexible elements, and flexible elements are basically two force members, but only in tensile. Okay, they cannot support compressive load. So the cables will apply a tensile load. It does not support any compressive load. And if you take a look at component AB, because there's only two pins that are connected to any loads outside AB. Therefore, AB is a two-force member. You have AB at point A and point B. Okay, we have point A and point B. They are two force members. Therefore, we know the direction of the force. So the direction of the force is in the direction of pins AB or the line AB and opposite direction. So we just draw AB without any external pins, then we have only two forces. So it's called a two-force member. So over here we have FAB acting on point A, the direction of B. This is FBA. Or to simplify things, this is in terms of magnitude, this is equal to FAB. So we know the direction. We can find the direction. Okay. But if we were to draw another free body diagram, so we have A here, so we have FAB. Now at point B, if we apply the pin, now that's the pin there at point B. And we have the external load which is applied through the pin. So that's 1200 kilonewtons. Sorry, newtons. And we have remember the cable? And there is a cable CB. So there is F, B, C. Now we know the direction of BC from the geometry. We know the direction of the component itself. Therefore, if we know all these directions, then we can find or we can solve for if that is x and that is y. So we can solve for FAB and FBC. Okay. So you just use equations of equilibrium. From the free body diagram for AB, so we have B here and A here, we have FAB, and we have 1200 and FBC. So from the previous calculation, we can get FBC and FAB. But the question says find the internal forces at point D. So point D is somewhere in between A and B with a vertical height of 0.6. So what we need to do then is to draw the section free body diagram. You can take the section at D and take it from A, or we take it from B. So you can have one of the two diagrams. If you take it from B, so what we then have is, right, that is the section, that is point D. Okay, now that is B, and B we will have FBC and also 1200 newtons. So at the cross section we have three components. We will have a normal component, we will have a shear component, and we have a moment about point D. So we have VD and D and also MD, right? However, we can also take the section diagram from A. So if we use from A, what we then have is, now that is point A, and we have FAB. Now at the cross section D here, so we still have point D there. We have a normal, see, opposite direction. This is ND to the lower left. This is ND to the upper right. Okay. And the shear here VD is downwards, so here is upwards VD. And the moment here is counterclockwise, so we have a moment here which is clockwise. So we have MD. Okay. So you can use either diagram, either of the two diagrams, to solve for the internal forces at point D. Now from these two diagrams here, we can see that the simpler one will be taking from A, because you only have FAB, right? And from this diagram here, you can find quickly that VD is equal to 0. So we can find that this is equal to 0. Okay, and MD is also equal to 0, because taking moment about point D, you only have MD and there's no other forces in the equation. Summation of MD is equal to 0 for the bottom diagram. You will have MD is equal to 0. Okay, so the moment is equal to 0. You are left with one more, which is ND. So summation of forces in the x prime direction is equal to 0, saying that that is x prime. Okay, so we then have is FAB plus ND is equal to 0, or ND is equal to FAB negative. Okay, so that we get ND. If you go using the top diagram, which is from B, you will have a longer equation, because you have FBC and 1200 newtons, which are not in the same direction. And to find ND and VD and MD, you cannot simply say VD is 0, because you don't know the effect of these two FBC and 1200 newtons on the direction of BD. So you have a longer equation to solve that problem. Similarly, in this example here, we can see that there is a two-force member. If you look carefully at point B and C, point B and C are pin joints. And component BC here has only 2 points where external load is applied to the component, and there are pins. Therefore, BC is a two-force member. So this here, we know that this is two-force member. Okay. So when we know that it is two-force member, we know direction of the force that is applied on the points B and C for that component. Or in other words, the load comes from component AB. Therefore, when you draw free body diagram of component AB, you know that the direction of the load from BC is in the direction of the line BC. Okay. Whereas component AB is not a two-force member because you have 3 points or location where you have external loads being applied. So the first load is applied at point B from component BC. The second point is at point A from the support bracket at A. And the last point is where you have the moment acting at the point. Okay, so AB is not a two-force member, whereas BC is a two-force member. So normally you don't need to draw two-force members because it doesn't help very much. But for AB, if you draw free body diagram of AB, so you have A and you have B. Okay. Now, because AB is not a two-force member, you don't know direction of the force at A. But because BC is two-force member, we know direction of the force. So we know that force there and we know the angle. Okay, whether it's a horizontal part or the vertical part of the angle. Then we know that at this point here, which is 100 mm from point A, you have a moment 70 Newton meters, and you want to find at point D. Doesn't matter, that's the second part. Therefore, at point A, you will have two components. We just assume any direction, doesn't matter. So we have AY and AX. And using this free body diagram, okay, this is FBC. Using this free body diagram, we can solve the problem, right? If you take moment about A, so the first step will be taking moments about point A is 0. You'll find that you only have this 70 Newton meters clockwise. So we can just assume, let's say this is clockwise, is positive, right? So we have 70 Newton meters is clockwise. Then you have component of FBC. The vertical component will give a moment about point A. The horizontal component will not give any effect in terms of moments. Okay, so this FBC component is going upwards, right? So it's going counterclockwise about point A, so minus FBC times the angle, so that's sine theta, if we call this is theta, okay? And the distance is the length AB. The length AB in our question is 400 mm. So times 400 mm, right? Or because we are using meters, you can convert that into meters, which is 0.4 meters. Okay. and this is equal to 0. So you have to convert this into meters, which is this is equal to 0.4 meters. Okay, and from this equation you can get F BC. So here we can get F BC. Okay, so once you've got FBC, you can solve for AX and AY. That is if you want to do that, right? Otherwise, to solve this problem at point D, you just draw free body diagram of the section. So in this case, we need to draw free body diagram of the section at point D. So what we do is, we draw from the right. If you draw from the right, so that's point B. So we have FBC, okay, acting at point B. We have 70 Newton meters at the point there. You know the direction or the distance from the question given. And at point D here, this is point D, we have the section, okay? And at the section, for solid objects, we have three components. We have the normal component. We can assume to the right or to the left, doesn't matter. We have a vertical component, so we have N, normal force. We have V, which is a shear force. And we have a moment, M. So these are all at point D. So MD, ND, and VD. Okay. So from this free body diagram of the section, we can then find the value for ND, VD, and MD. The moment component, the shear component, and the normal load component, which are internal loads to the component AB. They are acting internally, so they are called internal loads.